Good morning, everyone, and thank you for being here. Welcome to the presidential address of Rosa Matzkin, the outgoing president of the Econometric Society. It is a real pleasure for me to introduce Rosa today. Rosa is the Charles Davidson Distinguished Professor of Economics at UCLA. Before joining UCLA in 2007, she held faculty positions at Yale and Northwestern, and she has received too many honors and awards to list them all, but just to mention a few, she's a member of the National Academy of Science, the American Academy of Arts and Sciences. She's a fellow of the Econometric Society and a founding fellow of the International Association of Applied Econometrics. Rosa is a co-editor of the Handbook of Economics series and of the 7th volume of the Handbook of Econometrics. She has previously served as editor-in-chief of Quantitative Economics, as associate editor of Econometrica and of the Journal of Econometrics, and as co-editor of the Research Monograph series of the Econometric Society. Now, even though Rosa is keen on economic measurement, her service to the Econometric Society has been immeasurable. In addition to her editorial positions, she has served on the Executive Committee, on the Council for North America, and on the Regional Standing Committee for Latin America. Rosa's research represents very well what the Econometric Society stands for. The Econometric Society is an international society for the advancement of economic theory in its relation to statistics and mathematics. And indeed, the signature of Rosa's contributions is the strong link between econometrics and economic theory, and the intent to avoid specifications or transformations not implied by economic models. I think it's interesting to revisit how this approach came about. And when you hear Rosa tell the story of how she became an econometrician, it's really a story of passion. But Rosa and econometrics did not fall in love at first sight. As an undergraduate, she was dissatisfied with the fact that many of the regression models she saw seemed to rely on ad hoc assumptions. So when she started her PhD in Minnesota, she initially wanted to be a theorist, and she trained as one. For example, one of her 2 job market papers, which she published in Econometrica, introduces axioms of revealed preference to characterize choice data generated by maximization subject to nonlinear choice sets. And these apply to a wide range of models, including models with monopsony powers, models where consumers face regressive or progressive taxes, etc. Now, during grad school, however, Rosa was also exposed to the work of McFadden and others who were relaxing parametric assumptions, and she saw a way in which she could develop econometrics using theory. And that has become Rosa's fundamental contribution to the field. I like this story because I find Rosa's journey really inspiring for young scholars today. PhD students sometimes feel the urge to define who they are from the very beginning and to fit squarely within a certain field or set of topics. And Rosa's experience shows that being open to the ideas and the methods that economics at large can offer may lead to path-breaking work. In her career, Rosa has developed methods to test whether the data are consistent with economic models, methods to identify and estimate non-parametric functions using shape restrictions implied by theory, non-parametric methods that allow unobservable variables to enter the model in non-additive ways, and methods to identify and estimate non-parametric and non-separable systems of equations. As you will see in Rosa's lecture, the one that she's about to give, her work can be understood as an attempt to relax constraints or assumptions by exploiting insights from theory, and in particular, relaxing parametric specifications on functions and distributions, relaxing assumptions of separability on unobservables, and relaxing independence conditions. But let me stop here and not take more time from Rosa's lecture. which will take us through some of her contributions on the identification of economic models. Thank you, Rosa.
Thank you, Eliana, for your very kind words. It's a pleasure to be here presenting the presidential address of the Econometric Society. But before that, I would like to thank several people. First, the ASSA for the organization of these meetings, then the Econometric Society Program Chair, Alessandro Pavan, the Econometric Society Program Committee that did an incredible job in the program, the North America Region Secretary, Jeff Ely, and the North America Region Committee members. The Econometric Society Technical Meeting Planner, Ritu Johori, the ASSA meeting organizers, Gwen Loft and Rebecca Loft, and for the fantastic year I had as president of the Econometric Society, I would like to thank the executive vice president of the Econometric Society, Bart Lipman. Every morning I would have emails from him with lots of things that he has been working on. And the executive director of the Econometric Society, Lynn Hogan, for having been a constant source of support and advice. So I'm very, very thankful to them. I would also like to thank the executive committee members and the chairs and members of the many committees for their so extremely valuable work that they do for the Econometric Society. Also, as Eliana said, I was fortunate to find a place in the Econometric Society where I could present and develop my work, and there are many people that supported me through my career. I would like also to thank them. So I will start with the presentation which is going to be on the identification of economic models, one of the main topics I have been working on. And as Eliana was saying, my work has been trying to relax assumptions that have been used without finding a source in economic theory. So I thought that using economic theory, one can allow to relax these assumptions. So I started working on relaxing parametric specifications, on functions and distributions. Then I relaxed separability assumptions on unobservable variables. And finally, I relaxed exclusion restrictions in the models so that we can consider situations where many variables depend on many other variables and they interact between them. So it's simultaneous equation models, which was the source actually of how econometrics started. If one when the Coles Foundation started, it was the Coles Commission, they set up of people to try to understand how the economy works, how to build models. Coles, in the beginning, they put people together to work on trying to understand price indices, but then when they saw that they actually needed models, so they gather theorists and statisticians, and they work on developing models for the economy. And monograph number 10 develops the methods of simultaneous equations, because the interaction between the endogenous variables was a very important situation that they had to consider. So I see my latest work, and actually I'm going to present some of what I consider to be a very close extension to what they have done, relaxing as much as possible assumptions. So just to introduce the topic, linear separate. So the standard textbook models are y equals x prime beta plus eta, where it's assumed that eta, the expectation of eta given x, is 0, and then interest lies on beta. Having observations on y and x, one tries to get the value of beta. Now, of course, one can think, well, why linear? That imposes a lot of restrictions on the model. So there has been work, of course, relaxing that, and that's the non-parametric separable models, where the conditional expectation of y given x is assumed, basically has very weak conditions, very weak properties, kind of continuity, let's say. And then one can obtain, using the same observations, y and x, one can obtain the function s. Now, the models I've been working since the late 90s is a non-separable model. In this model, we observe y and x. So y is the dependent variable, x is the variable that is, comes into the system, but is determined outside the system. And epsilon is an unobservable variable. Okay? And this is an approach that takes the model, the economic model, and just basically wants to say what's observable and what's unobservable, and then tries to get the values using just what's known about the function m. Okay? But in contrast to this model, where we separate the model, in the sense we say, well, this function mx epsilon can be written as some conditional expectation of y given x, and some other function that depends on x and epsilon, and which has been, is done here. This is the conditional expectation, but then eta is the one that contains all the information about the interaction between the observable and unobservable variables. And this is treated as a second kind of stage, but not, most of the attention is in this function Sx. So one can think of, we have a model, and we just label variables. I mean, we just determine what's observable and what's unobservable. And then if we transform the model, we get the model, the second model. If we don't transform it, we get the third model. So both are consistent with each other, but in the third model, we can exploit much more the theory, the restrictions from economic theory, because M is an economic model that just basically says how x and epsilon determine the value of y. This is a model that is specified just for what's observable and what's unobservable. It depends on what's observable and unobservable, which is okay to analyze, but it doesn't, when we transform the model into the separable one, we're losing all the information of the, I mean, most, hopefully not all, but we're losing a lot of information from the economic model that we can use when we study this model, the third model. Okay, so that's the approach I have been taking. And I'm going to talk on, for sure on one, and hopefully in the second one, on two models. One is how to identify marginal utilities when when individuals choose a vector of products, but it's, I will talk about hedonic models, so we can think of a product as being a vector of characteristics, and individuals choose the characteristics, the product that maximize their utility. Individuals have different preferences, which depend on this unobservable epsilon, so everyone has a different value of epsilon, and we only observe one price function. Instead of the standard reveal preference approach, where we recover the preferences of an individual by looking at how the individual makes choices on different budget sets. In this case, we observe each individual making just one choice, and we want to get their, his or her marginal utility, the value that the individual gives to the, in this case, attributes. So y is, in this case, then the solution of the maximization of a utility function that depends on y, let's say the vector of characteristics, x are some observable characteristics of the individual, and epsilon is the unobservable taste. And epsilon will be multidimensional. And so this is the price that for the vectors of characteristics, and we observe each individual. For each individual, we observe the characteristics x, and of the individual, and y, the choice of the individual. Okay? So y and x are observable, epsilon is unobservable, it's a vector. Py is the price function is known, that's observed, and the utilities are known. And given the distribution of y and x, this method recovers the derivatives of the utility function for each individual. Okay, sorry. The second model that I hope I get to is the simultaneous equation model, which is the model that was specified in the monograph number 10 of the Coles Commission. So we have vector-wise that depends on all the other variables, and each one has some exogenous variables, x1 up to xk, and an observable variable. So it's a system of simultaneous equations with non-separable random terms, unobservable terms, sorry. And so the functions m are unknown, epsilon is unobservable, y and x are observable, and given the distribution of y and x, which is what we can observe, we want to recover the derivatives of these structural functions with respect to all the endogenous and exogenous variables that enter into the functions. Okay. So this is a model I have been working on under some restrictions, and I hope to present results that where the functions m are homogeneous, locally homogeneous of degree 1. Okay? But rather than using a parametric restriction on these functions, which is used in many models, and especially applied work, I will show how one requires minimal assumptions to be able to recover these derivatives. Okay. How do we do for questions? Do you want me to leave some? Okay. Maybe. Fine. Okay. 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 So first, just an introduction to semi- and non-parametric methods. So as I said, the semi- and non-parametric methods are relaxed, or try to relax parametric specifications on functions and distributions. And given if one has to specify something, some assumption that is ad hoc, then the results will also be kind of, we cannot trust very much the results if they depended on assumptions that, cannot be justified other than for computational capabilities or something else. Non-parametric methods approximate well almost any function. So one can use them if one is not sure whether the specifications are correct or not. One can estimate the model non-parametrically and then see whether it satisfies the shape restrictions or the restrictions that one imposes. So for example, one can test whether the model is linear or not. A local behavior can be uncovered with these models and not with the parametric ones, because since we are not imposing any restriction that is global, then if there is a hump in a function, one can get it with these methods. And it's easier sometimes to impose shape restrictions on these functions. Now, for estimation, there are two questions that one asks. One is, what's the appropriate model? And that's the connection between basic econometrics and theory. And then if one wants to estimate it, to take it to the data and to use it, then for non-parametric methods, we need a much larger data sizes. And also, they are usually more computationally intensive than estimating the beta from a linear regression. But we're doing well on that direction lately, so we're fine. So some references, so lots of people have worked on this. I guess in Econometrics, Matzkin 75 was the first that showed in polycotomous choice models that one can relax the distribution of the unobservable epsilons. In now non-separable models, as they say, they avoid transforming the original model. And then we have a more complicated model to analyze, but from the other side, the unobservable variables correspond to critical variables in the model, so we have a lot of information about them, which we can exploit. Then they are going to enter in non-linear, non-additive ways, but we can exploit the structure. And as I said, we have information, and it's consistent with the model, the separable model. Some references on simultaneous equations. So as I said, in the monograph number 10, Leo Hurwitz specified a non-additive model with a linear, it was like a linear model with unobservables being the coefficients of the endogenous variable. McFadden, in his 85 presidential address, talked about non-separable models, and there is some literature that, and I hope I didn't miss, but I'm sure I miss people, so sorry, and you can send me emails. And for non-separable, that is non-simultaneous, there is a very large literature. Now, I'll start from a very simple model that I worked on in 2003. So consider a worker that is assigned to work X hours. OK, so here. So suppose that we have this model, y equals mx epsilon. Suppose that X is the amount of hours a worker is assigned to work. And epsilon is the unobserved productivity of the worker. Y is the output. Okay? And we're interested in the function M, the production technology of the worker. So we might want to know, for example, so one possibility is, of course, to separate the model and write it as V of X plus eta, but that will lose all the information of the individual. We want to get the individual's production technology so that we can know, for example, what will be the output of this worker if we assign rather than 8, 9 hours. Okay, so it could be mx prime E minus mxe. So we observe the worker, the output at X hours. We want to get the output at X prime hours for this particular worker. So this can be done with these methods. Okay, so if with a separable model, you can't, right? Basically, you are going to get the average output, the average output of all workers that were assigned 8 hours. Here, with this, analyzing this model, leaving it intact, then we can recover the function M, some measure of the productivity, and the derivatives of this production technology. And if we want to calculate to know the average, we can do that too. Okay. So the main equation, I would say, in the scalar case, that allows us to recover this individual function is this one. Okay, where we have, okay, here. So this is, I'm just going through the equation. So this is the probability that epsilon is, so assuming independence, the probability that epsilon is less than or equal to E is the same as if we condition or uncondition it on different values of X. And now because of the strict monotonicity, so M is strictly increasing, output is strictly increasing in productivity, so we can, the event epsilon less than or equal to E is the same as the event M of X epsilon is less than or equal to MXE once we condition on X. Once we condition on X, X is not a random variable anymore, so this is just the function of epsilon, and this is the value of the function when epsilon equals E. Okay? But now the M of X epsilon, now if we consider it as a random variable, is just the output Y. So we get that this event, this probability equals the probability of output being less than or equal to the output of this worker conditional on X. So if the 95 percentile, if the worker has a productivity in the 95 percentile, the output of the worker will be also in the 95 percentile. That's basically what this equation says. So we have now, okay, and this is in Matzkin 2003. Okay, so now we have this equation, but this equation holds on this side, f epsilon of E, it doesn't depend on X. On the other side, we have two functions that depend on X, the conditional distribution and the function mxe. So, but since this equals this function that doesn't depend on X, so we can have this equality. We can just vary the value of X, and it's going to be the same. So we have this equation, and now you can see here, MXE is observed, is the output of the worker. This is a distribution that is of observable variables, it's observed. This is also a distribution of observable variables, that's also observed. So in this equation, the only unknown is MX prime E. But then we can just, if this is strictly increasing, then we can just obtain MX prime E, right? So we get this equation. So we can obtain then the output of the worker with productivity E at hours of work X prime. Okay. So this can, one can also ask, well, okay, so we have this difference. How, if we want the actual output, the actual production function, how do we get it? So let me. Okay, so if we want the actual production function, we will need to add an additional restriction. So one possibility would be to say that the production technology is constant returns to scale on array. It doesn't need to be constant returns to scale everywhere, just on array, which means constant returns to scale is homogeneity of degree 1. So we can specify the value of the function at one point, and then employ the fact or the assumption that if we multiply x bar and epsilon bar by lambda, the output will also be multiplied by lambda. Okay, so we have this. And then under this assumption, if we are willing to assume that output is homogeneous of degree 1 on the inputs, then we can obtain the function m and the actual value of the productivity of the worker. So we have on this side the distribution of y given x, and on this side we have the distribution of epsilon. So the first thing we're going to do is obtain the distribution of productivity. So we know that at y bar, when we look at the distribution of y conditional on x bar y, right? So we know we specify the value that was epsilon bar. So and that the equality between the two distributions, the distribution of productivity and of output given x, they were equal, right? So we have this equality, which is this line. So we look at this, the green distribution of y given x here. At y bar, when we look at, for this distribution, we have in the distribution of epsilon, epsilon bar. So we got already the value of the distribution of epsilon at epsilon bar because of the assumption of imposing a value on the production function at one point. And now, if we multiply inputs and outputs by lambda, right, we also know the value of the function because it's just the value of the function is just multiplied by lambda. So we can have an equality between when y, the output is lambda y bar, and we look at the distribution of output conditional on hours of work equals lambda x bar at lambda y bar. So here again, we have the equality, we get this point. Okay, so now we know what's the distribution of productivity at lambda epsilon bar. So varying the values of lambda, we get the whole distribution of productivity. We actually get a value for the productivity of the worker. And then once we have, here, okay, so in the equation, so we have this equation. Okay, now we know this function. Okay, so if we know this function and this is observed, then now we can get this one. Okay, so we can recover the whole production function of the workers for hours of work, for any hours of work, and for any productivity. Okay, so this function is, once we know this, so we have a functional equation with two known functions and one unknown function. We solve for the known function, which is the production function, and basically we get it. Basically. Okay, so once we look along the array to get the distribution of epsilon, everywhere else we don't need the production function to be homogeneous of degree 1. It can have any shape, and we are going to get it, as long as it's increasing in productivity. Okay. Another possibility is to use this specification, where y equals m of x, and epsilon, the unobservable, enters added to some observable variable z. And again, we can impose, m has to be invertible in it, so we can impose monotonicity. So and we assume that epsilon is distributed independently, again, of x and z. And if we impose again the value on the function, so now t bar is z plus epsilon. So we can do the same. So we're varying the values. So when at y bar, and if we look at the distribution of y, just let's say forget about x, just think about z equals t bar minus e2, which we can choose. We can decide the value of e2. So z is observed, t bar is chosen by us, and e2 is also chosen by us. So we look at this distribution at y bar. Again, we look at the quality, so we get the distribution of epsilon at e2. And continuing looking for another value. Instead of E2, we take E1, so we have this value. And we, again, look at the equality equation and get the distribution of the productivity at E1. Continuing like this, varying the values of E2, we get the distribution of epsilon at all values. And once we have the distribution of epsilon and the distribution of y given x, we can recover the function m. Okay. So this is in an old paper of mine. And it's basically these two assumptions I have used since one of my first papers in Matzkin 92, where I relaxed the both parametric assumptions in discrete choice models. If consider a situation where the endogenous variable is just 0, 1, an individual takes an action, if the utility of taking that action, which is given by Vx minus epsilon, is bigger than or equal to 0. So we observe this, the probability that an individual with characteristics x will take the action. It can be written like this. So we can get both functions to be recovered from the distribution of y equals 1 given x by imposing constant returns to scale on this function, doing something similar to what I did, but now it's easier because we don't have the non-separability. And then also this assumption, Vx plus z. The second assumption is also I used it in 1992. Okay, so again, if we specify here the value of v at x bar, then since this is known, and here we have f epsilon of z, varying z, we get the distribution of epsilon. Once we have the distribution of epsilon, we can recover Vx plus z. We know z, then we can recover Vx. Okay. So I'm going, in simultaneous equations, one can more or less do the same, but the problem is more complicated because we have dependence across the variables. So y1 depends on y2. Think about the standard example is demand and supply. So y1, the demand, depends on y2, the price, characteristics of the consumers, observable x1 and observable epsilon 1, and the price asked by producers is a function of the demand, y1. It depends on how much they have to produce, y1, characteristics of the firms, and epsilon 2, observable and unobservable. Okay? So in equilibrium, what we observe is when these two equations are satisfied. But these functions depend on, so if we want to know what will be the demand of consumers for a price that has not been yet observed, we need to know what M1 is. So for different values of y2, we want to get the function M1. So, and similarly for producers, if we want to know what the output of producers is going to be for the price that producers are going to ask for a particular output, y1, we need to know this equation M2. In terms of expressing these functions of, where on one side we have variables that come in the system determined from outside and variables that are determined within the system, y1 and y2 are the variables that are determined within the system, and they are non-parametric functions that depend on the observable variables and unobservables that enter in all the equations. In the linear simultaneous equation models, the epsilons are added. And so when one adds, so these equations become linear, and the epsilon 1 and epsilon 2 enter as in one functions, added to the linear functions of x1 and x2. So these are the reduced form equations, are linear in the x's, and they have an added scalar that is a linear function of epsilon 1 and epsilon 2. So now we have a model, a function that depends on many unobservable variables, and we are interested in getting this function. Okay? So one can have x2 for both, or this is a situation where we don't have observable variables for M1, but we do have for M2. Okay, and then in this case, again, the reduced form function will be non-separable in the unobservables that enter into all the equations. So this is in the linear. One usually tries to get the relationship how y and x influence epsilon, or how epsilon can be written in terms of the observable dependent and independent variables, or endogenous and exogenous variables. So in the linear model, we have something like this. In the non-parametric, we're going to have a non-parametric function that depends on y and x. So one can ask, okay, so this is a big system. How do we getting all these functions might be complicated. We don't, in many cases, we don't need to get the whole functions. We might just want to get some particular element of them. So one can think of about the model where we have y is the dependent observable variables and x are observable exogenous, y are endogenous, and we might even have endogenous variables that are unobserved, y star, okay? And they will depend on, we can include the functions or parameters into two sets and then think about what conditions do we need to get the true element, the element that generated the observations in S1, okay? And so, we can say that an element, so suppose that we have these two elements, so we can say that one is identified if no matter what other values the element in S2, we're going to get something different. So that's one definition of identification, but the one I'm going to use, which is equivalent, is where I can show that the element can be uniquely recovered from the distribution of the observable variables. So if you give me the distribution of observable variables, I'll tell you how to get some element in the model that I'm interested in getting, no matter what the other things are, okay? Okay, now in this case, the equation for simultaneous equations, the equation that provides us an equality between the distribution of epsilon and the distribution of the observable variables, it's this one rather than one with the distribution functions. One has to look into the probability density functions. Okay, so the probability density of y given x, which is given by this, by the transformation, assuming invertibility, by the transformation of variables equation, is the distribution of the density of epsilon evaluated at the value of epsilon given by this function r, and then this is the absolute value of the Jacobian determinant. And the reason for this is think about the epsilon 1 and epsilon 2. So epsilon 1 depends on y1, y2, and x1. Epsilon 2 depends on y1, y2, and x2. And we observe y1, y2, conditional on fixed values of x. We observe y1, y2. To those values, there correspond an epsilon 1 and epsilon 2. The equilibrium epsilon 1 and epsilon 2 are here. So this is the values of epsilon 1, epsilon 2 that will give you the value of y1 and c1. And this is the values of epsilon 1, epsilon 2 that will give you y2, because y1 and y2 depend on both unobservable variables. Now, if we want to look at the probability that y1 is less than or equal to c1 and y2 less than or equal to c2, in this, that corresponds to this region in the set of epsilon 1, epsilon 2. Okay? And the distribution, the probability that epsilon 1 is less than or equal to this value, epsilon 2 is less than or equal to this value, is this whole, is the area limited by the green lines. So there is no equality here. However, if we just vary a little bit the values of y1 and y2, right? So we're going to get the red and blue lines get shifted a little bit. And then we have here the probability that y1 and y2 are within this neighborhood. And this is the area of this region is the absolute value of the Jacobian determinant. So this equality is satisfied in the equality of the conditional densities, the conditional density of y given x. This is the value of epsilon, the density of epsilon at the value of epsilon that corresponds to the observed y's, and this is the area of that that we obtained, the area that we obtained for the in the densities. Okay, this one. Okay. So now again, we have an equality, a functional equation where some functions are unknown, some functions are known, and we can try to see what we can solve within that equation, considering different models which are given by economic theory. So different restrictions from economic theory can be used for that. So some examples so in 2015, I wrote a paper where I used these particular specifications. This is similar to the z plus epsilon in the one-dimensional case. So now we have x1 plus epsilon 1, x2 plus epsilon 2. And then I show how to recover these functions, M1 and M2, using this specification. Okay, and so in that case, so rather than having one t bar, we have s t bars, but we have epsilon plus xj is this function, x enters additive, and then in this equation, the absolute value of the Jacobian determinant doesn't depend on x, which is very helpful. And here we have the density of epsilon evaluated at t bar, which is something we choose, and x, something that we observe. So varying the value of x, we can recover the density of epsilon. And once we have the density of epsilon, then we can go back to trying to get the functions m easily. Okay. So in I'm going to talk, as I said, on two models. One is using this to obtain non-separable preferences in hedonic models. Okay. So in hedonic models, we have a situation where firms produce products. Products are characterized by characteristics, and individuals choose the product, choose the vector of characteristics that maximizes their utility. So it's different than the work by Hauthacker, Usawa, De Breu, and integrability conditions or the reveal preference conditions. So in that case, we get the preferences of the individual by making the individual face different choices and then seeing what the choices are. In this case, we just have one budget, and then individuals locate along this budget, depending on their preferences. And this is P of y, which is observed. Okay, so we can ask questions about how much consumer is willing to pay for the increased product quality, wage premium that we need to give a worker to increase the on-the-job fatality risk, or how much homeowners are willing to pay to avoid moving 1 mile farther from work. Hedonic models have been studied since the work of Kort. The related references to my work are these ones where, so NAWM and Chernosukov, Galishon, Henry, and Paz consider multi-dimensional hedonic models. So this is the problem faced by the consumer, and the consumer maximizes preferences. So we get a function, y star, that is some non-parametric function of the observable and unobservable characteristics of the individual. So they satisfy the first order conditions, and the problem here is that have only observations on one market, and if x is determined and epsilon is determined, this doesn't vary. So what we need to identify a function, to recover a function, is independent variation in each of the coordinates and to see how the value varies. If when we fix the values of 2 of the coordinates, the value of the third one is determined, then we cannot obtain this function. We cannot recover this function. So, so in a paper with Heckman and Lars Neschem, we show how to do this using some of the restrictions of in Matzkin 2003. So basically, we need a dimensionality reduction that will allow us to get the marginal utility. So as I say, there is 2 papers, but one can, using this method, the methods for simultaneous equations, recover the utilities for different specifications of how the endogenous variables and the epsilons enter into the utility function. So if we have, the consumer choosing now rather than one product, it chooses a vector of products, y1 up to yk, sorry, a vector of characteristics, y1 up to yk, and each of them is multiplied by the taste. Then we have a function that depends on that, okay, and up to epsilon k. Now, when the individual solves this problem, the choice of the vector of characteristics is going to depend on the taste for all the characteristics, not just for the taste of the particular characteristic. So we have, again, a system of simultaneous equations, where all the endogenous variables depend on the unobservables of all the other endogenous variables. And one can use one of the restrictions, the x plus epsilon, right? So we have, if we specify that the epsilons are some unobservable minus an observable characteristic. So we observe something on this unobservable taste that some observable characteristic of the consumer that affects the value. Okay, so individuals with, let's say, some particular characteristic, they vary on their taste, and which is this omega k. Okay, but they have some, xk will be fixed for them, and then omega k is going to change, and we get different values of epsilon k. So we assume that we observe x, and we observe the choices. So just for simplicity, just not to write too many equations, so suppose that there are only two characteristics. So this will be the utility of the consumer. The unobservables epsilons are these omega k's, which is an observable minus xk. The choice of the vector of characteristics of the consumer is this function that now depends on these things, and which is like the reduced form function of the method I developed in 2015, under an assumption that we have invertibility between the y's and the epsilons. So given y's, we have a unique vector of epsilons. We can then consider this system of simultaneous equations. And then the omegas, which are not observed, are this unknown function r of the choice of the individual plus x. So under an assumption on the density of these unobservables, then we can recover, and you can ask, well, how do we know whether this is satisfied or not? Well, the condition on the densities of the unobservables is satisfied if and only if this condition on in the density of the observables is satisfied. So once we have this, now we can obtain each of the coordinates was epsilon times the optimal choice. So we can fix the values of this, multiplying the epsilons times the optimal choice. We just fix that they are arbitrary. We can choose T1, T2, and so on. And then we can identify the marginal utilities at these values, T1, Tk, using the first order conditions. So I'm not going to take you through, okay. So basically, we can get an expression for the marginal utility, which just depends on the derivatives of the price function. We use the choice of the individual, and this is an E that we obtain from here. Okay? So, so this is observed, this is chosen by us, so we can find the vector E that satisfies this, and then we can get this. So we get the marginal utilities. Okay, good. So this is the first model. In the second one is one where I relax the linearity. Yes, basically I allow from the linear model, I go to a non-parametric one, where I can also use this functional equation, okay? But I want to impose a local homogeneity of degree 1, which is an assumption that is commonly used in simultaneous equations. Linear models with additive random terms, of course, satisfy this assumption, and many others. But rather than imposing the condition everywhere, I will only impose it on an array. So the one property we can exploit is that if M1 and M2 are homogeneous of degree 1, the inverse functions are also homogeneous of degree 1. And homogeneous of degree 1 have this property that multiplication by lambda of the arguments multiplies the output, the value of the function by lambda. Derivatives along the ray are constant, and the second order derivatives are 1 over lambda. So we know the values of derivatives and second order derivatives of functions that are homogeneous of degree 1, and we can exploit that in the functional equation. Okay, so this is the equation. So if we multiply y2, x1, and epsilon 1, then we get this. Okay, that's good. Okay. And we can assume homogeneity of degree 1, invertibility, and a rank condition similar to the one I had for the previous case. So just to go through one of the models, suppose that y1, we're interested in the derivative of m1 with respect to y2 when it's non-separable in epsilon 1, and we have this other equation. So think about supply and demand, right? So y1 is demand that depends on price and the taste of the consumers, epsilon 1, the price that producers ask to produce y1 when the input costs are x, which are observed, and epsilon 2 is the productivity, which is unobserved, is given by this function. And we're interested in the derivative of m1, we're interested in m1, okay? So the inverse system is going to be like this, that gives the value from the endogenous and exogenous variables to the unobservable variables. And as I said, these are homogeneous of degree 1. Now, if we look at the transformation of variables equations, so this is the absolute value of the Jacobian determinant that depends on derivatives of the functions R. Derivatives are constant, for homogeneous of degree 1 functions, are constant along a ray. So this is, again, if we move along a ray, this is going to be constant. These functions, when we move along the ray, moving along the ray, I mean multiplying all the variables by a lambda, okay? So these are going to be multiplied by lambda. If R1 of lambda y1 lambda y2 equals lambda R1 of y1 y2, okay? And the same here. So again, we have some information on a line from where we can recover this density of epsilon 1, epsilon 2, or at least as much as we need from it. Okay? And on this side, we have the density of y1, y2, which is conditional on x, which is observed. So here we have something that is observed. Here we have two functions that are unobserved. Okay? The vector of R1 are two functions, and this density. So if we take logs on both sides and then take derivatives, okay, so logs because we have multiplication, so log of this equals the log of this plus the log of this second term, and then take derivatives with respect to the y's and the x's. So I'm going to use g sub lambda yj to mean this derivative, and g of lambda sub lambda x to be this derivative. Okay, so it's the derivatives along the ray. Then how do we do to identify this? Well, because I'm not going to take you to the proof, but one can get this expression on the logs, and similar technique of trying to see what can be recovered from them. Then one can show that, so we look at y1, y2x, multiply by lambda, and the derivatives of the density of y given x at those values of y and x. So if we can find two values of this lambda along a ray, so we're looking along a ray, so if we find two values where this is satisfied, okay, so lambda star and the derivative of the log of the conditional density of y given x at the lambda star y1, lambda star y2, lambda star x1, lambda star x2, sorry, they only have one x, lambda star x, and where this equality is satisfied, then we obtain an expression for the derivative of m1 with respect to y2. So we can recover the derivative of the demand of consumers with respect to price, non-parametrically without making any other assumptions that is linear homogeneity. Okay? So if we find these 2 points on the line where this is satisfied, then this expression can be obtained in this way, okay, which is just looking at the difference, right, of the, rather than having the lambda x, we have lambda y1 and lambda y2. Okay. While this is good to show that we can recover it, if you have a lot of data, then it's fine, but usually we don't have that much data, so we want to use as much information as possible. So we might want to say, well, what happens if I have more than these lambdas, or what if the lambdas do not satisfy this? Can I use that information? And in fact, you can. So we're going to consider this equation. So this is an expression that can be obtained again from that functional equation. Here, everything is observed other than the beta, gamma, and C. Okay? And beta is the one, what we're interested on. Okay? So this is just give me all the densities, all the derivatives of the log of the density for all the points along the line, and then I'll use all of them to get to recover this beta star, this element that I want. And then using all of them, we're going to get something that has smaller variance. We're using much more of the observations. So the expression then for this beta star, this derivative, is going to be now an expression that depends on the derivatives along the whole ray. Okay. Okay, great. If we can also have a model with x1 and x2. In this case, we can get the derivatives of m1 and the derivatives of m2. Okay, again, because if the functions are homogeneous of degree 1, then we can we know that the derivatives along the ray are constant. And in this case, we are going to have matrices rather than just an equation. And but again, so here we need 3 values of lambdas, such that this matrix has rank 2. Okay. And then we can recover the derivatives of m1 and m2 with respect to y1, y2, and the x1s and x2. Similarly, we can use all the information, but I didn't write it down. But we also have, we can obtain we can use all the information of the observations along the ray by using a similar equation to the one with one ray, but didn't want to put too many more equations in the slides. Now I talk about the recovering the derivatives of these functions, but we can also get the value of epsilon, and epsilon1 and epsilon2. To get them, we just need to specify the value of the function at one point. So if we specify the value, then we can get the epsilons, the values of the epsilons too, if we need them. Okay, so this is what we can get without making any assumption other than the homogeneity. So in this sense, this is I see this as the best we can do when we look at the linear model, simultaneous, the 1950 standard model of linear simultaneous equations. What can we do to relax the additivity of the epsilons and the parametric assumptions? Then this allows you to basically use just the homogeneity of degree 1 assumption, which they made, and only with that, you can recover everything else, in a sense. So that's so we can have demand and supply functions, which are very nonlinear. As long as they are homogeneous of degree 1, we can get them. We can, and we don't need them to be separating with the epsilons or anything. So, and the conclusion is, I hope I convince you that the non-separable models are a good way of taking advantage of economic theory. We can recover the elements of models that have non-separable unobservables, exploiting the restrictions of economic theory. And also I gave you some examples where these elements can be constructively identified, so that given a distribution of observable variables, one can recover the elements we're interested on. And even though we might not be interested in recovering all the elements, just one, we can do that. Okay. So thank you all. Thank you.
I can break the ice with a non-technical question. That is, where do you see this line of research going, and what do you think are challenging, open questions that you would like to address that you haven't yet solved?
Well, I think there is a lot of very interesting things in econometrics. We can think increasing the models, allowing for many more. So in the terms of technical results, so increasing the number of equations and the variables that one can include in the model, that would be one of the directions I would go. I want to think about a mixture of models. And so we don't know what is the right model. So, and here I'm assuming that we know the model in a sense. So I'm not comfortable with that. I think that we don't know what the models are. So we want to consider a distribution of models and be able to see whether there is one model that is the one that is more appropriate, or just look at the distribution of models. So that's it. And of course there is work already on this, but I want to use my approach, which is much more flexible approach and allowing unobservables to be incorporated into the model exploiting restrictions of economic theory. So. But I also hope, of course, that it will, that applied people will use it. Actually, the paper that won the Frisch medal used Matzkin in 2003. So this was a model where the industry of shipping products. So there were we observed how many ships are at the port waiting to be hired to bring products from one place to the other. And we observed the number of contracts that are made to transport products, but we don't observe the firms that are interested in transporting food. So that was their epsilon. So Y was the number of contracts, X the ships that were at the port, and epsilon was the firms that were interested in having a contract. So we know that the number of contracts is going to be increasing in the number of firms that want to export products. And then using that and the homogeneity of degree 1, then they could recover that, the number of firms. So that was a single equation, but one can consider now contracts of many industries and many interaction between them, and then use the simultaneous, my latest result to that.
The parametric restriction with which I'm most familiar is quasi-linearity, that there's some variable usually interpreted as money in which payoffs are linear. Much of the theoretical work on hedonic utilities is done in the quasi-linear setting, and much of the theoretical work in mechanism design, principal agent problems, auctions. It looks like you're suggesting we ought to be able to just dispense with that.
Exactly.
Is that right?
Well, I mean, we could, yes. But yes, but I mean, it's the quasi-linearity, I'm kind of using it with the z's, the z plus epsilon. So that's one right. So that gives you a lot of identification power, I would say. We can also, though, if we want to include it and not have quasi-linearity and employ some other restriction, then we can do that too. Yes. Mm-hmm. Yeah. And actually in the paper with Heckman and NAWM, we do consider having it inside the model. Good, thank you.
So it might be a slightly of questions, but the constant return to scale in production function, usually we think that every input which affect output is all listed.
It's all,
so all
listed.
All
okay.
in the
right.
function. Therefore, that one is doubled, output is doubled. But
not with epsilon.
Yeah, suppose there are some limiting factor which is not observed. So some managerial capacity or span of control or something, and which is not doubled when the observed input is doubled. How you do?
Okay, so you say if you have an unobservable, but you don't have, it doesn't satisfy the homogeneity of degree 1. Yeah, so.
So the unobservable is doubled, then it's okay. But if unobservable is not moving together with the observable, then constant return to scale assumption is
right, in that case, I mean, yes, I am using the homogeneity of degree 1 to deal with these unobservables. So, so you would need to use some other restrictions. So like, for example, in the first model, the x plus epsilon, then there I didn't need the homogeneity of degree 1. So you could, so if you have some observable variable that you can attach to that unobservable variable, then you can do that. And you don't need the constant returns to scale on everything else either. So just basically, if you have the unobservable, just enters in a way added with something that you observe, then you're fine. Then you can do that. Yeah. Good.
Hi. I have a question about the estimation of the model using the observed data. So your identification strategy requires estimation of conditional distribution of y given x using observed data. But in practice, the dimension of x might be large. So one way to overcome is to assume additivity, like a kind of you have to introduce additional assumption to estimate these conditional distributions of y given x. But these assumptions are not from economic theory, so you have to introduce other assumptions to estimate the model, to implement your identification strategy. So what do you think about that?
Okay, so it depends what you're interested on, because so one could, non-parametric estimators, we know that they converge very slowly when the dimension of x increases, right? But if you're interested, let's say, on one derivative, then you can integrate out all that, so you don't need to impose the linearity, the additivity, or some other. You can just estimate the model and then integrate over the coordinates that you are not interested on, and then get, so that reduces the dimensionality of the problem. So as long as you can integrate over them, then then you're okay. So we're imposing, allowing them to be non-additive. As long as what you're interested on doesn't depend on the functional form in which y depends on all these vector, these high dimensions, then you're fine. Yeah, good. But in some cases you might not, so yeah, thank you. Good.
Okay, so thanks again, Rosa, for this very thorough, primer in Matzkin's Econometrics, and thank you everyone for participating.
Thank you. Thank you. Thank you. Thanks.